In this video, we'll understand the general notes provided in the anchor bolt plan and column detail drawings of a real pre-engineered building project. Many engineers focus only on dimensions and details, but the general notes contain critical engineering instructions that directly affect fabrication quality, anchor bolt installation, foundation accuracy, welding requirements, material specifications, and overall site execution. We'll explain every important note in simple language, understand why each instruction matters, and learn how these notes help prevent costly mistakes during construction. By the end of this tutorial, you'll be able to confidently read and interpret the general notes before starting fabrication or erection work. So let's begin with the first engineering note. This is the first general note of the drawing, and it is one of the most important notes that every engineer, detailer, fabricator, and site engineer must understand before using any drawing. The note clearly states, all dimensions are in millimeters and all levels are in meters unless noted otherwise. This means that every length, width, spacing, plate size, bolt distance, and structural dimension shown in the drawing must be read in millimeters. For example, if a dimension is written as 5,000, it means 5,000 millimeters, not 5 millimeters. Similarly, all elevation values such as foundation level, finished floor level, roof level, or top of steel are measured in meters. For example, if the drawing shows plus 6.500, it means an elevation of 6.5 meters, not 6,500 millimeters. Misunderstanding these units can cause serious fabrication errors, incorrect surveying, and costly construction mistakes. Therefore, before starting fabrication, surveying, or site execution, always verify the drawing units and carefully read the general notes. Understanding this first note correctly ensures accurate interpretation of every drawing used in a PEB project. Now let's understand the second general note, which is one of the most critical instructions in every PEB project. This note states that the entire steel structure has been designed and detailed only for the loads specified in these drawings. That means every column, beam, rafter, purlin, girt, brace, and connection has been calculated according to the approved design criteria. The note also clearly mentions that no alterations to the structural system are allowed without prior approval from the design engineer. This includes removing any structural member, adding new members, modifying existing connections, changing the building layout, or placing additional equipment and loads that are not included in the original design. Even a small modification can change the load path and affect the overall behavior and safety of the structure. Therefore, before making any structural changes during fabrication, erection, or future building modifications, approval must always be obtained from the project designer or structural consultant. Following this general note helps maintain structural safety, ensures compliance with the approved design, and prevents costly mistakes during construction and future operation of the building. Now let's understand the third general note, which specifies the surface protection requirements for the steel structure. This note states that all steel framing members, except bolts and fasteners, must receive a two-coat epoxy paint system after proper blasting. Before painting begins, the steel surface must first be cleaned by blasting to remove rust, mill scale, dust, oil, and other contaminants. A clean surface allows the paint to bond properly with the steel. After blasting, the first coat of epoxy primer is applied to provide corrosion protection and strong adhesion to the steel surface. Once the primer has cured, the second epoxy coat is applied to improve durability, weather resistance, and long-term protection against moisture and corrosion. It is important to note that this requirement applies only to steel framing members such as columns, rafters, beams, purlins, girts, bracing members, and other structural steel components. The note specifically excludes bolts and fasteners because they are normally protected using a different surface treatment specified elsewhere in the project drawings. Following this general note ensures a longer service life, better corrosion resistance, improved appearance, and reliable structural performance throughout the life of the pre-engineered building. Let's move to general note number 4. This note explains how to identify different types of bolts used in the project. According to the drawing, high-strength bolts must have a yellow dichromate finish, while machine bolts must be electrogalvanized. This color and surface finish help engineers and site teams quickly identify the correct bolt during fabrication, inspection, and erection. High-strength bolts are designed to carry critical structural loads and are generally used in primary steel connections. Machine bolts are normally used for secondary connections where the specified design permits their use. Using the wrong bolt type at any location can reduce connection performance and may create serious safety risks. Therefore, before installation, always verify the bolt type, surface finish, project specifications, and drawing requirements. Correct bolt identification is a simple step that helps ensure safe, reliable, and code-compliant steel construction. Now let's understand general note number 5, which explains one of the most important requirements for high-strength bolts before tightening. According to this note, all high-strength bolts must be properly lubricated and kept free from dust, dirt, and debris before installation. During tightening, the nut should rotate smoothly from the snug-tight condition until the required bolt tension is achieved without damaging or stripping the threads. If the erection team finds that the factory lubrication is insufficient or has been removed during handling or storage, the bolts must be lubricated again at the construction site before final tightening. Proper lubrication reduces friction between the bolt threads and the nut, allowing the required preload to develop accurately. It also prevents thread damage, ensures uniform tightening, and improves the long-term performance of the steel connection. Never tighten a dry or contaminated high-strength bolt because excessive friction can produce incorrect bolt tension, leading to unsafe structural connections. A small amount of proper lubrication can make a significant difference in achieving safe, reliable, and code-compliant bolt installation. Let's continue with general note number 6. This note specifies the machine bolts that must be used for all secondary steel connections in the project. According to the drawing, every secondary connection shall use 12 mm diameter electroplated machine bolts conforming to ASTM A307, unless noted otherwise in the detailed drawings. Secondary connections include components such as purlins, girts, sag rods, bracing accessories, and other non-primary structural members where this specification is applicable. The electroplated coating provides protection against corrosion, while the ASTM A307 standard ensures the required mechanical properties for these connections. Using the correct bolt diameter, coating, and standard helps maintain proper fit-up, reliable fastening, and long-term durability of the structure. Never replace these specified bolts with different grades or diameters unless the engineer's drawings specifically allow it. Following this simple requirement ensures every secondary connection performs exactly as intended throughout the service life of the building. Now let's understand general note number 7, one of the most critical instructions in the entire drawing. This note clearly states that the correct type of bolts must always be used exactly as specified in the engineering details. Every bolt in a steel structure is selected based on its required strength, grade, diameter, coating, and intended application. Replacing the specified bolt with a different type, even if it looks similar, can reduce the connection strength and affect the overall performance of the structure. The drawing also warns that using the wrong type of bolts may result in structural failure, and the responsibility for such errors rests with the erection contractor. Before installation, always verify the bolt type, size, grade, coating, and project specifications against the approved drawings. Never substitute bolts based on availability or convenience without written approval from the design engineer. Following this simple instruction helps ensure safe erection, reliable connections, and long-term structural performance. General Note Number 8 specifies the welding standard to be followed during steel fabrication. It states that all continuous machine submerged arc welding, commonly known as SAW, shall comply with the requirements of the American Welding Society Standard AWS 1.1-1996. Submerged arc welding is widely used in PEB fabrication because it produces deep penetration, high-strength welds, and consistent quality. During this process, the welding arc remains completely covered by a layer of granular flux, protecting the molten weld from atmospheric contamination. Following the AWS 1.1 standard ensures that welding procedures, welder qualifications, joint preparation, weld quality, and inspection methods meet internationally accepted structural requirements. Any deviation from these standards can reduce weld quality, affect structural performance, and increase the risk of failure during service. Therefore, every welded connection in the steel structure should be fabricated strictly according to the specified AWS welding code. General Note Number 9 explains the welding requirement between the web and flange of built-up steel sections. According to this note, web-to-flange welds shall be provided as single-side fillet welds, following the requirements of the AISC 9th edition, Table J 2.4, pages 5 to 67, unless noted otherwise in the project drawings. The web is the vertical plate of the section, while the flanges are the horizontal plates. The fillet weld joins these components together, allowing the section to act as one structural member and safely transfer bending and shear forces. Using the specified weld type and size is very important. Incorrect welds, insufficient weld length, or poor workmanship can reduce the load-carrying capacity of the member and may lead to structural problems during service. Therefore, fabricators must follow the approved shop drawings, use qualified welding procedures, and inspect every weld to ensure compliance with the AISC standard before the member is dispatched to site. General Note Number 10 explains the requirement for web butt welds used in built-up steel members. According to this note, web butt welds shall be complete penetration welds using a flux backup for plate thicknesses up to 16 mm, unless noted otherwise. A butt weld joins two steel plates end-to-end, making them behave like a single continuous member. A complete penetration weld means the weld metal extends through the full thickness of the joint, providing maximum strength and continuity. During fabrication, a flux backup is placed beneath the joint to support the molten weld metal. This helps achieve full penetration, prevents weld defects at the root, and produces a high-quality weld. This welding method is commonly performed using the submerged arc welding SAW process in controlled workshop conditions to ensure consistent quality. If complete penetration is not achieved, the joint may become a weak point, reducing the member's ability to safely transfer structural loads. Therefore, fabricators must follow the approved welding procedure, use qualified welders, and inspect every butt weld carefully before the member is released for erection. General note number 11 explains the welding requirement for flange butt joints in built-up steel members. According to this note, flange butt weld shall be provided on both sides using a copper backup. In addition, all flange plates having a thickness of 19 mm or more shall be beveled before assembly. The flange carries the highest bending stresses in a steel member. Therefore, the butt joint must develop the full strength of the plate without creating a weak point. To achieve this, the edges of thicker flange plates are first beveled. This groove allows the welding process to achieve complete penetration through the entire plate thickness. A copper backup bar is placed beneath the joint during welding. It supports the molten weld metal, prevents burn-through, and helps produce a smooth, high-quality root weld. The weld is then completed from both sides of the flange, creating a strong and continuous connection capable of safely transferring tensile and compressive forces. Proper edge preparation, correct welding procedures, and thorough inspection are essential to ensure the joint meets the required structural performance and complies with the project specifications. General note number 12 explains the material requirement for built-up steel sections used in a PEB structure. According to this note, all built-up sections must be fabricated from hot-rolled steel plates conforming to ASTM A36 specifications. The material must have a minimum yield strength of 250 megapascals, ensuring adequate structural capacity for carrying design loads safely. During fabrication, engineers should verify that the steel plates supplied by the manufacturer comply with the specified ASTM grade before welding or assembly begins. Using the correct material grade improves structural strength, durability, and long-term performance while preventing failures caused by inferior steel quality. Always verify the material test certificates and project specifications before fabrication starts. This simple requirement plays a major role in maintaining the safety, reliability, and quality of every pre-engineered building project. Now let's understand General Note number 13, which specifies the material requirement for purlins and girts used in a pre-engineered building. According to this note, all purlins and girts shall be manufactured from steel coils conforming to grade 50 material. The specified minimum yield strength is 345 megapascals, providing higher strength than ordinary structural steel while keeping the sections lightweight and economical. Since purlins support the roof sheets and girts support the wall cladding, selecting the correct material grade is essential for maintaining the building's structural performance under wind, dead, and live loads. During fabrication, engineers should verify that the supplied steel coils meet the grade 50 specification and that the manufacturer's material test certificates confirm the required mechanical properties. Using the specified material improves load carrying capacity, durability, corrosion performance, and the overall reliability of the PEB structure. Always ensure that purlins and girts are fabricated only from approved grade 50 coils with a minimum yield strength of 345 megapascals, exactly as specified in the project drawings and general notes. In this video, we have completed all 14 general notes of the PEB General Arrangement Drawing. We started by understanding drawing units and structural design limitations, then learned about epoxy painting, bolt specifications, lubrication requirements, and secondary connection bolts. Next, we covered the importance of using the correct bolt types, AWS welding standards, web-to-flange welds, web-butt welds, and flange-butt welds according to AISC requirements. Finally, we studied built-up section materials, ASTM A36 requirements, and Grade 50 material specifications for Purlins and Girts. These general notes are much more than standard instructions. They define the project requirements for fabrication, material selection, welding quality, corrosion protection, connection safety, and overall structural reliability. Following every general note correctly helps prevent fabrication errors, improves construction quality, ensures compliance with engineering standards, and delivers a safe and durable PEB structure. Thank you for watching this video. In this session, we completed a quick and practical overview of all 14 general notes used in PEB general arrangement drawings. You learned about drawing units, design requirements, framing members, bolt specifications, welding standards, material requirements, built-up sections, and many other essential fabrication and erection guidelines. These general notes form the foundation for understanding every professional PEB project and help avoid costly fabrication and site execution mistakes. In our next video, Video 20, we will begin a detailed explanation of the general arrangement drawing notes, one by one, using real engineering examples in a simple and easy-to-understand way. If you found this video helpful, please like, share, and comment with your questions or suggestions. Subscribe to ACP Civil Hub and press the bell icon so you never miss our upcoming PEB engineering tutorials. Thank you once again for your support. See you in Video 20.